Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 18th lecture, and this lecture should end the Chapter 6 information. We were talking about rectifiable curves in our on A to B, and I want to prove the only theorem I want to prove about it. Here's what it says. It says if gamma prime is continuous on A to B, then gamma is rectifiable and the length of gamma is equal to the integral from A to B of the absolute value of, or the norm of gamma prime of t dt. Okay. All right, here's the proof. Start off by looking at these values, x sub I minus 1, less than x sub I, less than or equal to b. And so these are two numbers in between A and B. Then by the fundamental theorem of calculus, this is part 2. The norm of gamma of x sub 1 minus gamma of x sub, I should say x sub I, and x sub I minus 1 equals to then the absolute value here of x sub I minus 1 up to x sub I of gamma of t dt, which is less than or equal to I shouldn't say absolute value, I should say norm. Excuse me, norm, which is less than or equal to the integral from x sub I minus 1 up to x sub I of the norm of x prime of t dt. So that's this first result is from the absolute from the fundamental theorem of calculus, and this is from the previous result. So so this length of gamma, I'm sorry, this lambda of the partition or gamma, which equals to the sum as I went from 1 to n of gamma of xi minus gamma of xi minus 1 will be less than or equal to the sum as I run from 1 to n of the interval of x sub I minus 1 up to x sub I of the norm of gamma prime of t dt. And this is true for any partition script P of A to B. which also equals, or so, I'll say this lambda of P gamma equals the integral from A to B of gamma prime T norm dt. And the reason is when you sum up over all these partition values, from x of I minus 1 to x of I, you get the integral from A to B. And this is true for any partition script P of A to B. Okay. What that tells us then is the length of gamma which is the soup of these overall partitions. Has to be less than or equal to this interval. Great. Remember, we're trying to show that this number, the length of gamma, is equal to this interval. And so the way we're going to do that is show this number is less than or equal to this interval, and then show that this number is bigger than or equal to this interval. So half the work. To show the other part, we will let epsilon be greater than 0 be given. Since gamma prime is continuous, on A to B, then, that being a compact set, gamma prime is uniformly continuous on A to B. So that means that there exists a delta greater than 0 such that for all T and S elements from A to B with absolute value T minus S being less than delta, then that absolute value, or the norm, of gamma prime of S minus gamma prime of T will be less than epsilon. Okay, so we let P be a partition of A to B such that the distance between consecutive partition values is going to be less than delta. Okay, so considering any Ti with x of I minus 1 less than or equal to Ti less than or equal to x of I, so anything in between the partition points, then the absolute value of Ti minus x sub I will be less than delta, and so the norm of gamma prime of Ti minus gamma prime of xi will be less than epsilon. Okay, working with this just a little bit, here's what we get. What this will tell us is that gamma prime of Ti will be minus gamma prime of xi in terms of norm. Well, let's write it down this way. This will tell us that the norm of this guy will be less than the norm of gamma prime of xi plus epsilon. There's some work to be done there, but that can be done. Okay. Thus, take a look at the interval from x sub I minus 1 up to x sub I of gamma prime of Ti dt. That's going to be less than or equal to from x sub I minus 1 up to x sub I of the norm of gamma prime of x sub I plus epsilon dt. And then that is going to be equal to, okay, these are constants with respect to t, and so what we get is that this is the norm of gamma prime of xi times the delta x sub I plus epsilon times the delta x sub I. And then that's equal to the integral from x sub I minus 1 to x sub I gamma prime of x sub I, this guy's dt, plus epsilon delta x sub I. Okay, that's equal to the norm of the x sub I minus 1 interval from x sub I minus 1 up to x sub I of gamma prime of t plus gamma prime of x sub I minus gamma prime of t dt plus epsilon times delta x sub I. Now, this is going to be equal to splitting this up as an integral from x sub I minus 1 to x sub I of gamma prime of t dt plus the integral from x sub I minus 1 to x sub I of gamma prime of x sub I minus gamma prime of t dt in the norm plus epsilon times delta x sub I. This is going to be less than or equal to, using the triangle quality, x sub I minus 1 is the integral from x sub I minus 1 up to x sub I, gamma prime of t dt plus the norm of the integral of x sub I minus 1 up to x sub I of gamma prime of x sub I minus gamma prime of t dt plus this epsilon times delta x sub I. This is going to be less than or equal to, well, should say just equal to. This integral right here, using the fundamental theorem of calculus, is gamma of x sub I minus gamma of x sub I minus 1 plus, we'll leave this alone, well, I'm sorry, let's make this less than or equal to. Let's make this change. And let's pull in these norms here. Pulling in those norms. Plus epsilon over delta xi. Now that's going to be less than or equal to the norm of the gamma xi minus gamma of xi minus 1 plus the integral from x sub I minus 1 up to x sub I of epsilon dt plus epsilon times delta x sub I. The reason that we got less than or equal to is I replaced the second integral in our previous line by the integral of this epsilon. And the reason I could do that is because when I was integrating the gamma prime of x sub I minus gamma prime of t, because the x sub I and t were within this interval of each other, then what's going to happen is that its absolute value, or its norm between that distance will be less than epsilon. So that's why I can make that replacement. And so this is equal to gamma of x sub I minus gamma of x sub I minus 1 plus, here, this will be 2 epsilon times delta x sub I. Because this integral is nothing more than epsilon times delta x sub I, because epsilon is a constant with respect to t. And so, the integral from a to b of gamma prime t in norm dt is equal to this integral from, using the partition, from x of 0 to x of 1 of the gamma prime t dt plus the integral from x of 1 of x of 2, the norm of gamma prime t dt, plus, and we keep doing this all the way down to having the integral of x of n minus 1 up to b, which is just x of n, of the norm of gamma prime of t dt. Which is less than or equal to, so this was a sum, so replace that sum by something bigger, each item in the sum. So that's the sum as I run from 1 to n of the gamma of x of I minus gamma of x of I minus 1, norm of that difference, plus we sum up this part as I runs from 1 to n, 2 times epsilon delta xi, and that is equal to, okay, so these sums of these gammas, that's nothing more than one of these lambda of p gamma, that's its definition, plus this is 2 times epsilon, can be pulled out, and then the sum as I run from 1 to n of the delta x of i's. We've seen that before. A lot of those changes in x of i's cancel with each other, and the terms do, and so we're just left with b minus a here. So from the previous line, because to get the lambda gamma, you take the sup of all such partitions. So this lambda gamma is going to be bigger than that, this lambda of p gamma, and plus 2 times epsilon times b minus a. Okay, and since epsilon greater than 0 was arbitrary, then we have that the integral from a to b of the norm of gamma prime of t dt is going to be less than or equal to this lambda gamma. And so, so we have that this integral is less than or equal to lambda of gamma. And previously, lambda of gamma was less than or equal to this integral. So that means that these two items must be the same. And that's the proof. Okay, what I want to switch to next is looking at series, numerical series. And we had done a little bit of that in chapter 6 because of the theorem. We needed some background work. But we're going to be talking about complex, a series of complex numbers. And so let's go ahead and start looking at this. And this is from chapter 3. So it's a little part we skipped from chapter 3. We'll look at numerical series. And so as a comment, unless otherwise stated, the sequences, let's say a sub k, we will be working with are complex, are sequences of complex numbers. And let's write down some definitions, preliminary definitions, to start getting some appearance about series. So it says, given a complex, or a sequence of complex numbers, a sub n running from 1 to infinity, then a sub n converges to a complex number. We'll call it A. If for each epsilon greater than 0, there exists a natural number n such that for all little n bigger than or equal to n, the absolute, or I'm sorry, the norm between a sub n minus a will be less than epsilon. That's the definition for a convergent sequence. And here, this norm is, of course, the norm in the complex plane. Another definition says, given a sequence a sub n of complex numbers, the infinite series of a sub n is the summation as n runs from 1 to infinity of a sub n, and we can expand this that just like a sub 1 plus a sub 2 plus a sub 3 plus, and you go on forever. Okay. Now the question is does this equal to a complex number or not? And so that's what our next definition addresses. Given a series, summation I'll write down as k runs from 1 to infinity. Well, this definition partially addresses it. Of a sub k, then the sequence of partial sums is S sub n, where f sub n is equal to the sum as k runs from 1 to n. So this is the nth term in the sequence of partial sums of a sub k. As a definition, a series, sum is k run from 1 to infinity of a sub k, converges to a number s if the sequence of partial sums call that f sub n converges to s. If the sequence of partial sums does not converge, then the series of a sub k is said to be divergent. It's said to diverge. Okay. First theorem about series, look at, states the series sum is k run from 1 to infinity of a sub k converges if and only if for every epsilon greater than 0 there exists an integer n such that for all n greater than or equal to m greater than or equal to big N, the complex norm as k runs from m to n of a sub k is less than epsilon. To prove this, we really need to concentrate on two things. So first of all, let me write down what to recall. There's the Cauchy criterion for convergence. When it says if x of n is a sequence of complex numbers, then x of n converges if and only if x of n is Cauchy. Next thing we'll look at is the definition of what it means to be Cauchy, a sequence of complex numbers. So a sequence of complex numbers is said to, let's give it a name, let's say X to the n. It's said to be Cauchy if for each epsilon greater than 0, there exists a natural number. N such that for all n and m greater than or equal to n, x of n minus x of m, the distance between them in the complex plane, usual complex matrix, will be less than epsilon. Okay, so really, the statement of our theorem is nothing more than the Cauchy criterion for convergence applied to the sequence of partial sums. We'll hammer out those details, write down the proof here. It says, let the sum as k runs from 1 to infinity of a sub k be a series of complex numbers let S of n and runs from 1 to infinity be the associated sequence of partial sums so that's kind of the header to our proof. Our proof is an if and only if statement, and I'm going to prove both directions, of course. This direction, suppose that this series converges of a sub k. Converges. We let epsilon be greater than 0 be given. Okay. So S of n, sequence of partial sums, converges. So that means that the S of n's are Cauchy. Because every convergent complex sequence is Cauchy. So there exists an integer J such that for all n and m greater than or equal to J, the norm of S of n minus S of m will be less than epsilon. So without loss of generality, we may assume n is bigger than or equal to n. So what we have is that the sum, when I look at this inequality, that the sum as k runs from 1 to n of a sub k minus the sum as k runs from 1 to m of a sub k Well, that's really equal to this norm as k runs from m to the smaller one to the bigger one of a sub k. And that's less than epsilon. And I made a mistake here. This is m plus 1. So that means there exists an integer, let's say n equal to j plus 1, such that for all n greater than or equal to m greater than or equal to j plus 1, or n, the sum norm as k runs from m to n of a sub k will be less than epsilon. So that's half the proof. Okay, going in the other direction, if we suppose there exists an integer, let's call it n, such that for all n bigger than or equal to m, bigger than or equal to n, the norm of the sum, k runs from m to n of a sub k, I'll explain, is less than epsilon. Okay? So that means there exists an integer, let's say L plus 1, such that for all n and m bigger than or equal to n, bigger than or equal to L plus 1. I called this L plus 1, but I meant to say n plus 1. That the sum as k runs from m plus 1 to n of a sub k will be less than epsilon. And here I can change this to m because of this fact right here. So bigger. Tell you the sign. Okay. So for all n and m, n bigger than or equal to m, bigger than or equal to n plus 1, if you look at s of n minus s of n minus 1 here, that's equal to the sum as k runs from 1 to n of a sub k minus the sum as k runs from 1 to m minus 1. That's going to be equal to this norm, the a sub k's here. This norm of the sum of the a sub k's as k runs from m to n, which we know to be less than epsilon. So, there exists a natural number and it's n, when we had before, such that for all n and m bigger than or equal to n, s of n minus s of m will be less than epsilon. We'll take the distance between them and complex plane. And so this says that this series converges. Because the sequence of partial sums was quotient. Okay. The next thing that I want to put up is something known as the divergence test. Here's what it says. It says if the sums k runs from 1 to infinity, the base of k converges, then the limit as k goes to infinity, is what I write, of a sub k equals to 0. It's called the divergence test because really its equivalent statement is that if this limit doesn't go to 0, then that series diverges. Okay. Here's the proof. Okay, suppose this series of AK converges. Then we're going to let epsilon be greater than 0 be given. We need a number, an natural number. N, such that for all n bigger than or equal to n, this norm of a sub n minus 0 will be less than epsilon. So we want the absolute value of the complex norm of a sub n to be less than epsilon. Since this sum as k runs from 1 to infinity of a sub k converges by the previous theorem, there exists a natural number, n, such that for all n bigger than or equal to m bigger than or equal to big N, the sum as k runs from m to n of a sub k will be less than epsilon. So here what I'll say is let n equal to m be bigger than or equal to big N. So as long as you're bigger than or equal to this number, particularly these two guys, then this really only has one term in it. We're going from n to n. And that's what we needed. So that concludes that proof. Ladies and gentlemen, that's all for this lecture, lecture 18. Thank you very much.